In a previous video, I demonstrated overfitting using a nonlinear regression or a polynomial fit and showed that as you include more and more terms, you overfit this data set here. And so in this video, I want to do the same thing but using a neural net. So I'm going to take this data here and start a new notebook here that I'm going to call Overfitting with a neural net. I should also take these things here, which I'm going to use, these libraries. Okay, so I'm going to take this data, and then I'm going to take the code that I wrote, the neural network code that I wrote for the handwritten digit recognition, or the MNIST data set that I wrote in a previous video. So I'm not going to take the data here. Well, let me just take everything here and then see what I need. So I'm taking everything from this cell and putting it here. I'm also using some functions which I have to remember to take as well. And so they're a little further up. Here, the activation function and the derivative of the activation function. And I'm going to put these in a separate cell. Okay, so now I have to sort of make these things talk to each other. So let's see here. So the x values I've already defined here. That's up here. I use x everywhere here in the code. So I'm going to rename the training set as, I'm just going to call the training set x and y. That way I don't have to change the names everywhere. And let's see, so here I have to scale the x values because I'm working with activation functions. So I have to remember to scale this. I played around with it a little bit before I made this video and found that normally I would scale this from between 0 and 1, but it actually works a little bit better to scale it between -3 and 3. And the reason for this, so if we look here at the form of the activation function, right, as we see, if we use very negative values or very positive values, you know, such as 4 or 6 or even 9, right, we're always going to get 1 in the activation function. So we have to pick a range here where the activation function is active, and I chose -3 to +3. So that's what that's how I'm going to scale my data set. Okay, so to do that, I'm going to divide this by 9, which is the maximum value. So now I have something from 0 to 1. Then I'm going to multiply it by 6. Now I have something from 0 to 6. And then I'm going to subtract 3. So now I have something from -3 to 3. And also for the y values, I found that it works better if it's just going from 0 to 1. And the reason for this is that this is actually, you know, a complete overkill to use a neural network on such a simple data set. So it's numerically very, very sensitive to this. So this is why I have to do these things. Okay, so I don't need this anymore. And I have my y values, so I have that defined above. So I don't need this. Okay. So let's see. So my input nodes. So that's my data. Now let's look at the neural net. So number of input nodes now is just 1, right? I want to feed it 1 x value and I want to get 1 y value back. So that's 1 in the input and 1 in the output. And then, you know, 100 hidden nodes is probably also overkill, and so I'm gonna change that to 10. Okay, so the next thing now is that the code that I wrote for the MNIST data set, right, is a classification code. So I want to get outputs between 0 and 1. Here I'm going to use, I want to use regression, right? And so in principle, I should be able to get any kind of output, right? So not just between 0 and 1, but really any value. So I have to change my neural network a little bit. So I've tried to demonstrate that here. So on the left, you have the neural network, the classification neural network that we've implemented previously, right? So you start with some input X, you send it through an activation function, right, in the hidden layer. So you get some output from the hidden layer, right? Then you again take a linear combination of that using a new set of weights, and then you pass it through the activation function, right, to get something between 0 and 1. Now here, right, I want to change the output node here so that I in principle can get any value. So what that means basically is that I take this set here as my output, right? So I no longer pass it through my activation function, so I simply set y predicted equal to this, right? So that's what I'm doing here. And so now, in principle, this can give me any value, not just between 0 and 1. So let's change that in the code. Right, so that's down here, so that's very easily done, right? I just take this and set it equal to the hidden output weights times the hidden y, like so. Now, of course, this is also going to change the backpropagation, so how I update them. Right, so let's talk about how I update these weights. Right, so my y predicted now is this. So my L2 loss, right, is the derivative of L2, right? So that's just the error times the derivative of y predicted with respect to the hidden outputs, right? And so that's just the hidden output, right? So the derivative of this term with respect to this term is just this term. The derivative of this is 1. The derivative of this with respect to w, right, is just this term. Okay, so that's my gradient for the hidden output. So, right, I don't need the derivative of the activation function anymore. And so I don't need these brackets even. Okay, so that's updating, or that's calculating the gradient for the hidden output. So let's look at the input hidden. And so, right, long derivation here, that the main point is that when I now again take the, when I take the derivative of y predicted now with respect to y hidden, I just get the hidden output weights back. So basically what that boils down to is I have to change the way I do the hidden error, right? There should no longer be a derivative with respect to the activation function, but just the weights. Right, so that's the hidden error here, right? And I remove the derivative of the activation function term. And so again, I don't need this bracket here. Okay, I also don't need this. I don't have to, yeah, this is labels. This has something to do with the MNIST data set, so I can remove that. Okay, now one of the final things is that for this kind of regression problem, again, like I said, it's using a neural network is a little bit overkill. So to demonstrate overfitting with this, I have to use a more powerful optimizer. So in a previous video, I demonstrated how the Atom optimizer is quite a bit more powerful than the gradient descent that we've implemented. And so I'm going to quickly implement that. This video is not really about the Atom optimizer, so I'm just going to cut and paste some code. So what I'm going to do here is I've written a function that gives me, using the Atom optimizer, gives me the change in the weights. Now that uses some parameters, which I have to include up here. So that takes the gradient and some parameters and calculates a change in the weights, in this case for the hidden output. So that's what I want to use here instead of the gradient, and the same for the input hidden. Okay, and the function itself I'm going to paste up here. So you may want to pause the video here and carefully look through the code. I'm also going to leave a link to the blog post that I based this implementation on. Okay, so I'm sure there's probably other things I need to change, but I think the best thing is just to run everything and see what errors I get and then go from there. So I'm going to go up to runtime and run all. Okay, and so I get some errors. Yes, okay. So it has some problems here with adding in the bias column. And so the reason for this is that I now no longer have a vector of numbers. I just have a one x value instead of 748 pixels. So I have to change the way I do this. So first of all, I just need a vector of just a vector of ones now, and I'm gonna put that in using this approach that I've used before. Okay, so that now I get just a vector, and now I just insert a simple vector in this. Okay, let's see what other error messages I get. Oh, that should be a small c. Here I'm actually working with matrices, and so when I do this here, my ones are not directly defined, right? Because I changed how I defined it up here. So I'm actually going to have to sort of redo this again and use, not redo, but just redefine what I mean by ones here. Okay, let's see. Okay, so the problem here now again is that my y predicted is a set of numbers, and my y values here is still a data frame. So I have to convert this into values. Let's see if that fixes it. Okay, so no error messages. Excellent. And I can see that the error goes down. So let's see if I can get it to go down even further. Let's give it 1,000 epochs. Okay, it looks like sort of it's flattening out here. Well, I'm using a very powerful optimizer. So let me actually decrease the learning rate a little bit. Right, the loss went down and it keeps going down. So let's try 10,000. Okay, going down, keeps going down. Let's try 15,000. Right, and so now you can see we've driven the error completely to 0. And let's see if we have overfitting. So in order to do this, I need, well, first let me plot. I can take this from the overfitting code. So let's try to plot. Oh, I'm calling my X train and Y train just X and Y. Let's see. Oh, yes. And I'm just calling this predicted. Right, so that is, as we can see here, that's a matrix. So I just want the first row of that. Oh, okay, and I haven't scaled, I forgot to scale my validation. So I'll multiply that by 6, divide by 3, divide by 9, sorry, subtract 3, and this needs to be values, and I need to divide this by 12. Okay, so that's, oh yeah, so that's my plot. Now I need, so in the previous code here, right, I need a new set of x values, so 100 x values. So let's copy this as well. And now I want to go from -3 to 3. And here now my f of x, right, I now want to predict using the neural net. Using the neural net and my x and y validation. Okay, so I'm going to have to make a function from this. So I'm going to call this y predicted validation. All right, so that's what I want to plot here. Okay, and so that, right, that's basically, I'm going to use this code here. So let's see, so I'm going to make a function. I'm going to grab this code. And I'm going to make a function here, which I'll just call predict, I guess. Okay, and so to do this, I will need XP, so where the bias is added. What else do I need? I need the weights, both the hidden output and input hidden and hidden output. And then I can return y predicted. Okay, so I'm going to grab this. And add that here, and that's predict. Oh. So I'm going to go up and change that here as well. In fact, I'm just also going to run it while I'm at it. Okay, so that's predict. Now, okay, so I need to add the bias ones here. So I'm going to grab this code here. And actually, I can just shorten this a little bit. I'm just going to put that in here. I'm going to work with small x, and my n is 100. And I don't need this, and I'm going to call this small x p, small x p, which I'm going to pass in here, and then I'm going to get it. So let's, oh, and then I have to plot it. That'll give me, okay, so I have to, yes. That'll give me a matrix just like it did before, and I just want to use the first row. Okay, fingers crossed, let's see. Of course. Right, it's complaining about this line, which uses an n, which it doesn't know what that is. So, right, we need to calculate that, and that it will be the length of my XP. Okay, fingers crossed again. Okay, excellent. So there we are. We can see there's, if I run at least 15,000 epochs, right, then we definitely have some overfitting going on. Okay, so in the next videos, I want to talk about how to, what to do about that when you're using a neural net.